Dear students, so welcome to today's lecture. So today we will start basic digital passband modulation and multi-level signaling. So far you have mostly seen binary signals with two levels. Okay, so today we will see if we, instead of sending just two bits 0 and 1, if we want to send a group of bits together as a symbol, then what are the implications of those? So in case of binary, you had zeros and ones, right? So you are sending the zeros and one as a single bit, and whenever you are sending a 0, you are sending a signal S1T, and whenever you are sending 1, you are sending a signal S2T. Okay, so now if you club, let's say, multiple bits together to form a symbol, let's say you have a binary stream like this, a random binary stream of data uh, appearing like this. So earlier you were sending bit by bit, so you were sending, when you were sending a 0, you were sending S1, when there was a 1, you were sending S2, again 0, you were sending S1, and so on. Okay, so now let's say if you want to club two bits at a time and send them as a symbol, so combination of two bits will have four possible cases, right? So you can have 0 0, you can have 0 1, you can have 1 0, and you can have 1 1. And let's say for each possible combination you send a signal S1, S2, S3, and S4. So see, the same concepts that you studied for signal space so far can be extended for multi-level signaling, where instead of sending one bit at a time, you are sending a symbol at a time, and each symbol can consist of multiple bits, and depending on how many bits are there in one symbol, you can have multiple signals sent out. Okay, so let's proceed. So far you have studied basics of probability theory, the signal space concepts, the Gram-Schmidt procedure, optimum receiver for binary communication through an AWGN channel, the matched filter receiver, effect of rotation of signal space on receiver performance, and probability of error calculations. And then also we saw a few binary passband communications, so BASK, BPSK, BFSK, etc. So so we will basically now extend our knowledge to multi-level signaling, as I just said. So multi-level signal. So you see, we designed an optimum receiver for a binary communication through AWGN channel. So we will do the same now for multi-level communication, and we will see how these aspects are represented in signal space, and then how to calculate the probability of error for multi-level signaling, and then what are the basic multi-level signaling schemes that we have for digital communication. Okay, so the first multi-level scheme is QPSK, which is quadrature phase shift keying. So the basic idea is that you have two signals, cosine 2 pi fct and sine 2 pi fct. Okay, where Fc is the carrier frequency, and you can see that these two are orthogonal over this interval. Okay, what does this mean? So this means that if you integrate over 0 to Tb cosine 2 pi, just a minute, sorry, cosine 2 pi Fct times sine 2 pi Fct, that this will be over dt, so this will be 0. Okay, but then there is another condition. So the Fc should be given by an integer multiple of 1 over Tb. Okay, so now since these two are orthogonal, this cosine and sine, you can transmit two different bits over the same frequency band at the same time by using these two signals, cosine and sine. So so basically you can have, let's say, you can define your phi 1 t as, let's say, cosine 2 pi Fct, and phi 2 t sine 2 pi Fct. Basically you have to normalize this. So phi 1 t is actually cosine 2 pi Fct divided by the energy, whatever the energy of phi 1 is. Okay, actually square root of energy, and same should happen for this. Then you can basically have two orthonormal basis functions just from this cosine and sine functions, because they are orthogonal. If you normalize them by dividing them with their square root of energy, then you also ensure that they are orthonormal, these two. And then you can have two axes, phi 1 and phi 2, you can define a signal space, and then you can transmit two different bits on phi 1. Okay, let's say basically you send two signals over phi 1 and two signals over phi 2. Okay, so you can have four different signals you can send for a combination of two bits. Okay, so you can have 0 0, and you can send S1. For 0 1 you can send S2, for 1 0 you can send, let's say, S3, and for 1 1 let's say you can send S4, and then these could be the four signals S1, S2, S3 and S4. Okay, so you are sending S1 and S3 over phi 1. Okay, and then you are sending S2 and S4 using phi 2. Okay, so basically you are sending these two signals S1 and S3 over the same carrier, that is your cosine, and these two signals are sent over another carrier which is 90 degree phase shifted version. So sine and cosine are 90 degree apart. Okay, or in other words, they are pi by 2 apart. Okay, and since they are pi by 2 apart, they are also orthonormal in terms of the vector representation. Okay, so this is the real arrangement that I was talking about. So if you have a bit pattern 0 0, you imagine that as message 1, and for message 1 you send signal 1, which is v cos 2 pi fct. For 0 1 you send message 2, and for message 2 you send your signal 2, which is v sine 2 pi fct. And for 1 1 you are sending message 3, which is essentially your signal S3, and this is minus v cos 2 pi fct. And then for S4 you are sending minus v sine 2 pi fct. So you can see that when you are sending the cosine signal, the amplitude of the cosine, so when you are sending the cosine signal, the amplitude is between plus and minus v, and when you are sending sine, the amplitude is also between plus and minus v. Okay, so plus v cos 2 pi fct minus v cos 2 pi fct. So this is your S1 and S3. So let's say if your phi 1, as I said, can be equivalent to the cosine signal. So you are basically sending plus v and minus v. So these are the two signals in the signal space that you are sending over phi 1 or the cosine signal. So these are your, let's say, S1 and S3 according to this. And then this is your sine or phi 2 axis, and over the sinusoidal signal you are sending again plus and minus v. So you have plus v and minus v, and let's say the plus v is your S2 according to this, and minus v is your S3. So and waveform wise this will look like this. So when you have 0 0, you have a cosine wave with amplitude ranging from v and minus v. When you have 1 1, let's say, then you have the same cosine wave but with a minus sign, which means a 180 degree phase shifted version. So it starts from here, okay. And when you have 0 1, you have the sine function, which is the 90 degree phase shifted version, so it's here. And then when you have 1 0, you have the minus sine function, okay. So in this way the time domain signal propagates depending on these bits. So if your bit combinations are changing, then your signals are also changing, and you are considering 2 bits at a time, okay. So in case of your binary, you are considering 1 bit at a time, and you are sending 2 signals, S1 and S2, depending on 0 or 1. Here you are sending 2 bits at a time, so you can have 4 possibilities of 2 bits, and you are sending 4 signals corresponding to those possibilities. So I already mentioned this. So the signal space representation of QPSK will look like this. So you have the phi 1 and phi 2 axis. So phi 1 is basically given by this, and phi 2 is given by this. So you can apply Gram-Schmidt also to verify that this is the case. But in general, since these cosine and sine are orthogonal, you can define phi 1 across S1 and phi 2 across S2, and then your S3 is here, which is basically your S3 is minus of S1, and your S4 is basically minus of S2. Okay, so these are the 4 signals of your QPSK set. Okay, and this is called quadrature phase shift keying because each signal you can see is 90-degree phase shifted version of the other. So if you consider the signal space from the perspective of amplitude and phase, let's say any point from the origin of the signal space to, or rather like consider any point in the signal space, and the distance of that point from the origin of the signal space gives the energy. Okay, so the distance gives the distance gives the energy, and distance gives the amplitude, and distance square gives the energy. Okay, so this each of these signals that are here, if you consider the distance of those signal from the origin, that gives the amplitude of the signal. Okay, and whatever angle the signal makes with the positive direction of the phi 1 axis, that gives you the phase of the signal. Okay, so the signal space representation also gives you the amplitude and phase of the signal. So when you are representing the 4 signals of the QPSK set like this, then you can see each of the signals are at a 90-degree phase difference with the other. Okay, so S1 and S2 are at a 90-degree difference, S2 and S3 again at a 90-degree difference. Okay, S3 and S4 again at 90-degree difference. Okay, so each signal is 90-degree phase shifted to one another. Okay, so that's why the term quadrature comes. So you have quadrature phase shift keying. Okay, and quadrature means you have 4 signals, and quadrature also means that you have a 90-degree phase shifted version of the signals. Okay, so or in other words, each signal is at a 90-degree phase shift from each other. Okay, so now moving on with this concept, if you now want to find out the optimum receiver for a QPSK system, so then what will be the case? Okay, so we will analyze this similarly to the binary scenario. So in the binary case, if you recall, we divided the observation space into 2 regions, like, so this was your R1, and then whatever outside was R2, and you had 2 signals, S1 and S2, which was transmitted. So if the received signal R falls into R1, then we decide that S1 was transmitted, and if it falls into R2, we decide S2 was transmitted. So that was the case for the binary communication. So in QPSK, we extend the same concept. We divide the space, the signal space actually, into 4 regions. So we have R1, R2, R3 and then R4. And each of these regions belong to the 4 signals. So S1, S2, S3 and S4. So now if your received signal falls into this region, then you decide S1 was transmitted. If it falls into this region, then you decide S2 was transmitted. If it falls here, then you decide S3 was transmitted, and then if it falls here, you decide S4 was transmitted. And then you can make a decision because you know the mapping of the messages on the signals here. So if you can figure out which signal was transmitted, then you can also figure out which message was originally transmitted. Okay. So in this case, like how will we calculate the probability of error? Okay, so since we have multiple regions, maybe it's a good idea to first calculate the probability of making a correct decision. So probability of making a correct decision is that given S1 was transmitted, if your received signal R falls within R1, then you make a correct decision. Okay, so this conditional density, if you integrate it by multiplying with the a priori probability, then you get a correct decision for transmitting S1. So this part, I mean this particular integral is the correct decision for S1. Okay. Similarly, this is the correct decision for S2. This one is for S3 and this one is for S4. So if you add all the correct probability of decisions together, then you get the correct decision for transmitting any of the signals. Okay, so so basically this correct decision is the union of, let's say, the correct decision for sending the ith signal where your I is from 1 to 4. Okay, so now if you take the probability of being correct, then this will be the sum of all the probabilities of taking a correct decision given a particular signal as I was sent. Okay, and these probabilities, these individual probabilities are these integrals. Okay, so this one is probability of correct due to S1, this one is probability of correct due to S2, this one is the probability of correct due to S3, and this one is the probability of correct due to S4. So if you can calculate this, then the probability of error can be easily calculated by 1 minus the probability of being correct. Okay, so so if you analyze this concept, so far what we have discussed here, you can see it's mostly similar to what we did for the binary case. Okay, so concept wise these are same. We are just extending this concept for a more number of signals, and in the binary we could calculate the probability of error directly. Here maybe it's a good idea to calculate the probability of being correct and then take the complement of that to get the probability of error. So also in case of the binary, we argued in a particular fashion that what will be the optimum decision rule that will minimize the probability of error. Okay, and from that argument we found that if certain condition is met, if something is greater than something, then we decide a 0 was transmitted. If something is less than something, we decide a 1 was transmitted. So similarly, if you analyze this probability of correct and apply the same rule as you applied in case of binary communication, you will get the optimum decision rule as this. So for the case of binary, so here we have I and j, and they range from 1, 2, 3, 4. So in case of binary, what we had was, if your P1 f of r given S1 t, if this term was greater than P2 f of r given S2t, then you decide that S1 was transmitted, and if this term was less, then you decide S2, or in other words, if this term was greater, then you decided that a 0 was transmitted, and then if this is less, then you decided a 1. Okay, so the same concept is applied here. It's a more general rule now. So you choose SIT if your PI times this conditional probability is greater than PJ times the conditional probability for SJ, where J not equal to I, and this J ranges from 1, 2, 3, 4. So basically you have to now check one by one and see if P1 f of r given S1, if this is greater than P2 f of r given S2t, or this. Or this. So basically, if P1 times this term is greater than all the other terms except one, so basically these are all your J's. So here in this case your I is 1 and your J's are 2, 3, 4. Okay, so you check whether your P1 is greater than all this, and then if that is the case, then you choose S1. Okay, now if your if P2 f of something, if this part is greater than let's say the all other terms, P1 times this, P3 times this, P4 times this, where these functions are like this. Okay, so so then you decide, or you choose S2. So you have to do a lookup like this. Okay, this is what is said in this this generalized decision rule. All right, so this is the generalized decision rule for higher number of signals. So you can simplify this decision rule as well by actually plugging in the distribution function. So your signals, the received signals will follow Gaussian distribution with mean Sj1 and Sj2. And why this is so, we have discussed this in the binary case. Same logic applies here. And then if you take the natural logarithms of both sides, then you obtain this. And then if you simplify, then the optimum decision rule yields that you choose SIT if your N0 log Pi minus these terms is greater than N0 log Pj minus these terms, where j is 1, 2, 3, 4 and j not equal to I. Okay. So if you further simplify, then you get again these rules. Okay, so you choose SIT if this side is greater than this side, where I not equal to j and j equal to 1, 2, 3, 4. So now if you want to have a receiver for this, so what you have is that you have your received signal here. You correlate and you correlate them with phi 1t and phi 2t, and then you take samples every ts seconds. So look, in case of binary, you are sampling every tb seconds. Here you are sampling ts seconds, which is equal to twice tb, because you are sending a symbol which is 2 bits wide. Okay, so your ts, which is a symbol time, is equal to twice over tb, the bit time. Okay, and here, since you are doing QPSK, you are sending 2 bits at a time with 4 possible signals. So in this case, you are sampling every 2 TB seconds or every TS seconds, and then you are computing these terms. Okay, so these terms you are computing, and you choose the largest, whichever is the largest. So you compute these terms for all the cases 1, 2, 3, 4, and you choose the largest of that. So if this term is largest for j equal to 1, then you choose S1. If this term is largest for j equal to 2, you choose S2, and so on. And then that is your optimum decision, which is the output of this circuit. And if, let's say, your input symbols are equally likely, okay, or in other words, if your P1 equal to P2 equal to P3 equal to P4, all the a priori probabilities are equal, then if all the a priori probabilities are equal, then you end up having this rule as the optimum distribution rule, and basically you are looking into this term, which is nothing but the distance of the received signal from the ith transmitted signal. Okay, so this term is the distance of the received signal from Si, and basically you choose Si if this is smallest. So again, this is your minimum distance receiver. Okay, so for QPSK also, you can see that this minimum distance rule applies. So you have 4 signals in the signal space, and if you draw a decision boundary, then the boundaries are these. Okay, so for S1 and S2, this is the boundary. And again, if you recall, the decision boundary for binary case for 2 signals was the perpendicular bisector of the line joining the two signals. So if you just consider these two signals S1 and S2, this is still the case. Okay, so your S1 and S2 is joined by this dotted line, and whatever is the perpendicular bisector is the decision threshold for S1 and S2. Okay. Similarly, for S2 and S3, this is the decision threshold. For S3 and S4, this is the decision threshold, and this merges with the decision threshold of S1 and S2. So basically, you just draw a continuous line like this. Similarly, for S1 and S4, this is the decision threshold which merges with the decision threshold for S2 and S3. So you draw a continuous line also here. So you can see that you have divided the signal space into 4 regions. So this is your region 1, this is your region 2, this is your region 3, and this is your region 4. And each of these region corresponds to one of these signals. So R1 is for S1, R2 is for S2, R3 is for S3, and R4 is for S4. And if your receive signal falls, let's say in R1, so if your receive signal R now falls here, then you choose S1T. Okay. If your receive signal falls here, then you choose S2T. If your receive signal falls here, then you choose S3T. And if your receive signal falls here, then you choose S4T. And this is how you have the decision rule. Okay. And just to mention, like this is also true for the binary case. I mean, in case I didn't mention this while I was teaching binary communication. So why would the receive signal fall here or here? Like what actually makes the receive signal? So let's say this one is your transmitted signal S1, okay, and S1, so your receive signal vector is basically your transmitted signal vector plus the noise vector, right? So if you are transmitting S1 and your noise is getting added to it, and if your noise is low enough, then after getting added to S1, your receive signal might have a component which falls within the close proximity of S1. Okay. So let's say this is your S1 vector, and let's say your S1 is along the phi 1 axis. So let's say your S1 has the components. So this is across the phi 1 axis, and let's say the phi 1 component is the amplitude of S1, let's say, which is square root of the energy of S1, and the phi 2 component is 0. Okay. So now after adding of noise, let's say your received signal has two components, R1 and R2. So after addition of noise, your R1 will be this, the phi 1 component of the signal plus the phi 1 component of the noise, and your R2 will be the phi 2 component of the noise, because the phi 2 component of the signal is 0. Okay. So based on this, if you plot your R1 and R2, okay, so let's say this term W2 is so high, okay, that, let's say this is my W2. This is my value of R2, which is equals to W2 now. And let's say my let's say my R1 component, which is square root of this plus W, is here. Let's say this is square root of E already, and this part is square root of E plus W. Okay, so this is my R1, which is square root of E S1 plus W. Okay, so now these are the two components of my received signal after addition of noise, let's say. Okay, so now if I try to plot the received signal, so this will be my received signal. Okay, and this received signal, whatever is dotted here, this falls within the region capital R1. So even after addition of noise, you can see that I can decide that S1 was transmitted. Now imagine a situation where this W1 component of the noise is negative, because noise is randomly varying, okay, and it can have plus or minus amplitude. So let's say this W1 component of the noise is negative for some reason. Okay, so if I add W1 with square root of ES1, and if it is too negative, then it might take this component of the received signal here. So this can be your new R1, which is actually square root of ES1 minus something, which is a very high negative quantity, because the W1 component is, let's say, negative. So in that case, my noise, my received signal will be here. Okay, because this is my R2 component. Let's say the R2 component is same, but R1 component is here because my noise is negative. I mean the first component of the noise is negative, and my R1 because of that falls here. So in that case, my received signal will be here, because this is the R2 component and this is the R1 component. So in this case, because of the negative noise, my received signal falls here in the region capital R2. Okay, even I have transmitted S1. So in this case, I choose S2 according to this decision rule, and I can make an error. Okay, but the reason to have this optimum decision rule is to minimize these possibilities, minimize these chances of errors. Okay, and if I have this optimum decision rule, then my chances of error gets reduced, and therefore the probability of error also gets reduced. Okay, or in other words, if I want to reduce this probability of error, I get this optimum decision rule. So they both are related to each other. Okay, so, and this is true for binary, for multi-level, for any type of digital communication. So this is for QPSK. So right now I am discussing QPSK with you. So let's move on. So you can have an alternative representation of QPSK like this. Okay, so let's say your original bit stream, okay, looks like this, which is denoted by AT. Okay, so this varies between -1 and +1. So when the binary bit sequence is 1, you have a +1 amplitude. When it is 0, you have a -1 amplitude. Okay, so this is your bit stream, and this is your message signal AT. Okay, now if you demultiplex the message signal AT into AIT and AQT, where your AIT only contains the even number of bits from the original message, and AQT contains the odd number of bits from the original message. Okay, so AIT is consists of A0, A2, A4 and A6, and the bit durations are doubled. So you take A0, okay, and you retain A0 for 2 bit intervals. Then you take A2, you retain it for 2 bit intervals. Then you take A4, whatever is A4 is 0 here, so this is negative here, and you retain it for 2 bit intervals. So in that way you construct AIT, and similarly you construct AQT by only taking the odd number of bits and retaining it for 2 bit intervals. Okay, so you have 2 separate tributaries of the original signal, and then you modulate the AIT with the cosine function, and you modulate AQT with the sine function, and then combine them together to get ST. So this ST is your QPSK signal. Okay, so so if you look into the 2 tributaries AIT and AQT, modulated with their corresponding carrier frequencies, they will look like this. Okay, and then the composite signal is the sum of these 2. Okay, and that will look like this. Okay, so you can write ST as this. Also you can write ST into this format. Okay, so these are this is the amplitude and phase representation, and this is the in phase and quadrature representation. So since this is the in phase and quadrature representation, this AIT and AQT, basically this AIT is the in phase term, and this is the quadrature term. So Q stands for quadrature, I stands for in phase. Okay, and then you can write like this also, where you have a phase difference theta t, and theta t is different for different combinations of AI and AQ. Okay, so this is again similar to what we discussed at the beginning of this lecture. So depending on the bit combinations for a 2-bit symbol, your phase of the signal is varying. Okay, so this is another alternative representation of QPSK. So this AI and AQ, these are the bits of the original symbol AT, right? So if you are taking the odd, you are taking the even bits as AI, and you are taking the odd bits as AQ. Okay, but if you look to the combination of these in the original signal AT, then you can see that AI and AQ are adjacent to each other, and based on that, if your AI and AQ are together 2 ones, then you have this phase. If they are 1 and 0, then you have this phase. If they are 0 and 1, it is this phase, and so on. Okay, So the idea is that depending on the combination of the bits um, in your symbol, where the symbol consists of 2 bits, you have different phases of the QPSK signal. And in the alternative representation also you can define the signal space like this, and you can still have the similar representation where we have 4 signals in the signal space defined by phi 1 and phi 2, and you have the distance of each signal from the origin as the square root of energy of that signal, or the amplitude of the signal, which is this term, and the angle it makes with the positive direction of the phi 1 axis is the phase of that signal. Okay, so for this signal, let's say we call it S1, the phase is pi by 4 and the amplitude is this one. For all signals, the amplitude remains the same because they lie on the circle of radius square root of v square ts, but the phases are different. So this signal makes pi by 4, this signal makes 3 pi by 4, this makes minus 3 pi by 4, and this makes minus pi by 4. Okay, and then the receiver for the QPSK will look like this. So where you are taking the received signal and correlating with phi 1 and phi 2, sampling them every ts seconds, and then you are checking whether the signal is positive, whether R1 is positive or negative. So if it is positive, basically to check that you are comparing it with a threshold 0. So if it is greater than 0, then you decide that your AIT is 1. If it is less than 0, then you decide your AIT as 0. Similarly, you can decide what was your AQT, and then you combine them together in the multiplexer to find out the final signal, which is AT. Okay, so so you can consider the in phase bit stream. So AIT is the in phase bit streams. Okay, and you are recovering in phase bit stream from the upper arm of this receiver, and you are recovering the quadrature phase from the lower arm of this receiver. So the in phase bit stream can be imagined as a BPSK. If you recall the constellation or the signal space diagram of BPSK, then BPSK signal space diagram looked like this. You had 2 signals which are lying across the same axis, and the one is 180 degree opposite of the other. So that means the signs are different. So if it is plus the square root of energy of this particular signal, then this is minus the square root of energy. So this is the in phase bit stream, which is 1 BPSK, and the quadrature bit stream is another BPSK. Okay, so you have essentially 2 BPSKs. So this is 1 BPSK and this is another BPSK. So 2 of these arms of the receiver actually correspond to 2 separate BPSKs. This BPSK is deciding whether S1T or S2T was transmitted, because S1T and S2T are transmitted with the in phase carrier, which was V cos 2 pi FCT, and S2T and this one, sorry, S2QT and S1QT was transmitted on the quadrature component, or sorry, V sine 2 pi FCT. Okay, so this is the quadrature bit stream, and you are recovering S1QT and S2QT from the quadrature bit stream, and you are recovering S1IT and S2IT from the in phase bit stream. Okay, so this is in phase and this is quadrature, or in other words, your phi 1t was proportional to the cos function and your phi 2t was proportional to the sine function. Sorry. So this was the case. So phi 1t was cos and phi 2t was sine. Okay, so so the basic idea is that QPSK can be considered as two individual BPSKs that are carried over two orthogonal carriers. Okay, and if you want to calculate the probability of bit error because of the QPSK, then basically any bit that is a part of this final signal AT can be in error because of either an error in this BPSK or an error in this BPSK. Okay, so the probability of bit error is equal to the probability of bit error for a BPSK with these parameters. Okay, you can see that both the in phase BPSK and the quadrature BPSK has these plus or minus square root of v square Ts by 2 as the energy of the signals, as the amplitude of the signals. So the error, the probability of error due to this in phase BPSK and the probability of error due to the quadrature BPSK are same, and that is determined by, again, a rule that you have already learned. So this is basically the Q function of the distance between the two signals divided by the noise RMS power. Okay, and the distance between the two signals in this representation is this plus this. Okay, because this is 0, so this distance is square root of v square Ts by 2, and this distance is also square root of v square Ts by 2. So this distance, the total distance, is 2 times the square root of v square Ts by 2. Okay, and if you put this in this formula, then you will get Q of v square Ts by n0, square root of the entire thing. Okay, so so the probability of bit error intuitively is basically the probability of error due to any one of these BPSKs which are making this QPSK, and that bit error is this, which simplifies to this. So probability of bit error. Okay, So this is actually very important to note. Okay, you are sending symbols here, and each symbol has 2 bits. So whenever you have such a scenario, when you have a symbol and you are sending multiple bits as part of that, then the probability of bit error means that what is the probability that one bit is at error. Okay, and you can also define probability of symbol error where the entire symbol is in error. Okay, which means, let's say if you are sending 00, this is the symbol in case of QPSK, and you are receiving 01. Okay, so here you see one bit is in error in this signal, but the entire symbol is in error. Okay, so symbol error and bit error are different when you have multi-level signaling. So here we have defined probability of bit error, and probability of bit error is same as the probability of bit error of any one of this individual BPSK, because if you are observing the bits, okay, here in this AT, that bit can come from your AIT or that can come from AQT. Okay, and these two are equally likely and independent of each other. So the probability of bit error for QPSK is same as the probability of bit error for any one of these individual BPSKs. Okay, but when you are talking about symbol error probability, then things are little different. Okay, and in case of symbol error probability, you are basically trying to find out that whether there is a error in the symbol or not. Okay, and for that, okay, let's go back to the previous slide again, and if you look into this receiver arrangement, okay, or rather let me go to a fresh sheet, and so so in case of probability of symbol error, let's say yeah, so if you have two arms like this and then you are correlating them with phi 1 and phi 2, and then integrating and then sampling at t equal to ts, which is equal to 2 TB, and then you are thresholding here, and then you are combining the two arms. So this one is giving you AI and this one is giving AQ, and this is your combined QPSK signal AT. Okay, so in such a scenario, the probability of symbol error, when you are looking at a symbol, that means you are observing 2 bits at a time. Okay, so in this case, okay, the 2 bits, there are 3 possibilities that can occur. Okay, and what are the 3 possibilities? That first bit is in error, the second bit is in error. So remember, this is the case of symbol error. And in QPSK, a symbol is 2 bits long. So a symbol can be 00, 01, 10 or 11. Okay. So if you look, let's say, into these received bits, and let's say you have transmitted this symbol, okay, and if you are not receiving this, then you are in error. So 2 bits, if you observe, and if those 2 bits are not 00 which you transmitted, they can be either this, this, or this. So this option is your option 1 here. Okay, so the first bit is in error. This option is your option 2. The second bit is in error, and option 3 is both bit are in error. Okay, sorry. Okay, so these 3 will have individual probabilities, and probability of symbol error is the sum of all these 3 probabilities. So probability that first bit is in error and the probability that the second bit is in error is basically the or let's approach this in this way. Let's say let's find out the probability that none of them are in error. Okay, so this probability is the probability of error due to this upper arm, as you just saw, is q function of square root of ES by N0. Okay, and for the lower arm also it is the same. Right. So so these are the individual BPSKs and they have this probability of errors. So probability that none of the bits in a symbol are in error is basically 1 minus this. Okay. So probability that there is no error in this in phase component is this, and the probability that there is no error in this quadrature component is also this term, and these 2 terms are independent, so they will be multiplied together and you will have this square term. Okay, so probability that none of the bits that you are observing here are in error is the probability that there is no error because of the in phase term and there is no error because of the quadrature term. And the error for the in phase term is the error of the BPSK because it is equivalent to a BPSK, and the error for the quadrature term is also the BPSK error probability because it is equivalent to BPSK. So probability that none of the 2 bits that you are observing here are in error is the probability that there is no error in the in phase term and there is no error in the quadrature term, and that can be found out by 1 minus the error for the individual terms, and since they are independent they are multiplied twice and you get 1 minus this term square. Okay, so all these three cases are complementary to this case. So this probability is the probability of symbol error. Okay, so probability of symbol error will contain these individual probabilities. Probability that first bit is in error, second bit is in error, both bits are in error, and that is basically equal to 1 minus the probability that none of them are in error. So 1 minus this term. Okay, so this is the probability of symbol error. So this is different from the probability of bit error. Okay, and if you summarize, if you simplify this expression is roughly equal to, so probability of symbol error if you simplify, if you just expand this square term, then this will be 2q of square root of this minus q square of the same term. Okay, so so this q function, this has a property that with if you plot it for es by n0, then the q of es by n0 falls very sharply as es by n0 increases. So for relatively high es by n0, or let's say relatively high signal to noise ratio, your q square term is much less than the q term. Okay, so you can ignore this part, and this can be approximately written as just twice q es by so so you can see that the probability of symbol error for QPSK is given by this, whereas the probability of bit error is given by just the q function. Okay, so this is q of square root of es by n0, and this is twice q square root of es by n0. Okay, So I will stop here for this lecture, and then I will resume our discussion in the next lecture. Thank you very much.